Good morning. I'm Chamodi Dissanayake, a fresh graduate from Med4, and currently I'm in the first year of my PhD. So today I'll be presenting the research from my master's thesis, LiDAR and photogrammetry for automated single-tree volume estimation. When we are talking about forest management, it is essential to have accurate and continuous forest inventories. For example, sometimes we need to measure DBH, tree height, and the volume of standing trees. But if we use traditional field-based methods, we have to face some kind of problems, such as, let's think if our forest stand is larger, we have to spend more time and cost for that. And also, there are some forest stands in mountainous areas, so there are limited accessibilities. And sometimes we have to do destructive sampling methods. So the problem is, do we have any solution for that? So in simply, I'll discuss the overview of my research study. I had a mixed forest stand with 9 plots, and then I collected data using 3 different sources. First of all, I collected data using traditional field inventory method, and then I scanned 9 plots using handheld laser scanner. And also then we flew a drone over the canopy to scan the whole stand. Then I wanted to extract the tree attributes and then create a model for predicting volume of single trees. Well, the primary objective of this research was I wanted to develop a model using HLS and drone-based metrics to estimate a stem volume at the single tree level. To achieve this primary objective, I had to go through 2 different objectives. First of all, I wanted to select the best open source tool to estimate or to process handheld laser scanning data, and then I wanted to select the optimal drone flight that I'll be discussed lately. So this was my study area, Ampudia in Spain. And to make our life easier, I created a flowchart for my methodology. So this research consisted with 3 different phases. In the first one, I processed handheld laser scanning data in 2 different methods, FSCT, and the cloud compare. After processing the data, I extracted tree attributes, and then I compared it with the traditional field-based methods, and then select the best method for the future process. And in the second phase of this research study, I had 2 different drone flights. The first one with 80% front and 80% side overlapping flight, and the second one was 80% front and 60% side overlapping flights. And we captured 2D images, and then we had to convert it into 3D point clouds, and then we extracted canopy metrics. Using these results, I wanted to develop a model to estimate volume at the single tree level. Well, these are some images that have been taken during the process. As you can see here, the point clouds, after getting the point clouds, we had to classify the point clouds and segment the trees into single tree level and extract the attributes. According to the results, we could identify both FSCT and cloud compare performed well in detecting pine wood and cypress, but there was a problem with oak. However, when we are talking about the DBH and the tree height, both FSCT and cloud compare performed well. Now, the problem is what happened with oak. Oak is a result of natural regeneration, and they grow as clusters. So in LiDAR or with point clouds, there are some difficulties in identifying these clusters. And during the first phase of this research study, I wanted to compare the stem volume. So I compared the stem volume calculated using Spanish National Forest Inventory equations, and I compared it with the volume we measured by FSCT. There was a problem with clear deviation with halepensis. We double check it and we triple check it. Maybe it might be the time to recheck a Spanish National Forest Inventory equations related with Pinus halepensis in Amphodia. So because of this thing, I continued the model development with Burgos equations only for the Pinus halepensis. Well, in the second phase of the research study, as I said, we captured images after flying the drones, and then these images were converted into 3D point clouds, and these are some point cloud results. Since we flew the drone from the above canopy, we couldn't get the DBH because it's kind of RGB images, but we could estimate the tree height using these drones, and it was kind of a satisfactory results. And in the third phase of this research study, we developed the model using stem volume and the LiDAR canopy metrics to estimate stem volume at the single tree level. These are the results. So we developed 3 different models for 2 different drone flights. In the first flight, we could achieve 0.76 R-square value, and the next one with 0.74. After creating the model, we can apply this model for the whole stand. That means it's with around 7,000 trees of the stand, and we can apply this model to estimate the stem volume at any single tree in this forest stand. Well, these are the conclusions. Both FSCT and Cloud Compare, they performed better in identifying and estimating tree attributes of pine woods and cypress. And there was a clear deviation in halepensis volume derived from National Forest Inventory equations, and Flight 1 showed the better performance. But now the problem is, when we are doing our research, how this alter from business as usual. Here it is. If you have a mixed forest stand, it's a bit difficult with the mixed forest stand, but how? If we have a mixed forest stand, we have to do a scanning of our plots and then fly a drone, maybe a bit cheap drone, to get some RGB images and create a model to estimate stem volume at any tree of your forest stand. So these are the future research steps. We need to find a method to identify the tree species, and then we need to find a solution for misidentification of tree stems, and then we can apply this model in forest simulation systems, as I mentioned, SIMAN4. So thank you very much. This research was supported by MED4.